Hello, it's Stat134, lecture 34. Last time we finished section 6.2. When x is a discrete distribution, we looked at the conditional expectation and the law of iterated expectation. Today we're going to review the properties of conditional expectations as well as get going in section 6.3, which I think is one of the most challenging sections in the book. Conditional densities, multiplication rule, and the rule of average conditional probabilities. So let's start with properties of the conditional expectation. So for a fixed conditioning event A, the conditional expectation is all the familiar properties of expectation. For example, the expectation of x plus y is the sum of the expectations. So when you restrict to an event A, that rule doesn't change because you're just restricting your outcome space to a smaller outcome space by conditioning on A. So there aren't going to be any surprises. When A is, for example, x is x, then the expectation of x given x is x makes x a constant, and the expectation of a constant is just the constant itself. So we can write that the expectation of x plus y given x is x plus the expectation of y given x. And that is an equality of random variables because left and right side are random variables. Then we have the properties shown here. The first is iterated expectation. That's an equality of numbers. The left and right hand side are numbers. And then we have the equality of random variables below, which we've essentially discussed above, the tricky one being 4 and 5, but they should be clear now. So next we start section 6.3, conditional density. Okay, so when x is discrete, conditional probability is just given by Bayes' rule. When x is continuous, now we have to make we have to condition on x in dx instead of x is x, but that's no problem. So we have Bayes' rule, and to define the probability of a given x is x, we need a limit as dx goes to 0 in sort of a calculus sense here. So, for example, if y is continuous and a is now y is in dy, we can write out a conditional density formula. So we have a new density, f y given x is x of y is the joint density over the marginal density. All the dx's and dy's cancel out here. This formula follows from basically Bayes' rule. So John Michael Laurel in our class, a great artist, made this picture of the conditional density. So you can think of it as a slice of the joint distribution along so you fix x in x and it make a slice along that line. And so the conditional density is a slice of the joint distribution, and you can draw the distribution along the dotted line here. I've drawn it below here in 2 dimensions. And so the probability that y is in dy given x is x is the area under the curve between y and y plus dy. So here's an example of a joint density, which is a constant times y minus x to the 8th. And I was hoping that you would remember that x and y are ordered statistics here. So you see the y minus x to the 8th power, so that makes you think that 8 darts are between x and y, and then 1 dart has to go in dx and 1 dart has to go in dy. So I know I have 10 darts. So x is the first ordered statistic, and y is the 10th ordered statistic. So that's that makes things a little bit easier, although there are other ways to do this. To find k, you could just also take the double integral, set it equal to 1, and solve for k, but this way is easier. So we just see right away that the joint density is 10 choose 181 y minus x to the 8th, so k is 90. And then to find the marginal, you're basically integrating out y, so you're integrating the joint from y is x to y is 1, and so you get 10 1 minus x to the 9th. Or a little bit more straightforward, I think, is you could just find the probability that x is in dx, which means that you have one dart in dx. Remember, x is the first ordered statistic, and that means you have 9 darts after x. So we get 10, choose 1, 9, 1 minus x to the 9th, which gives us the same answer. So then to find the probability that y is greater than 0.7, given that x is 0.2, one way you can do it is you're just finding the integral under the joint density, under the conditional density for y between 0.7 and 1. And so that's just a straightforward calculation. But you first have to actually calculate what the conditional density was using the joint density and the marginal density as I've shown here. Or, oh yeah, and so then you just calculate it this way. There is a second method, which is a little bit faster, but maybe less general. You can use the fact that x is the first order statistic and y is the 10th. So then, so first I'm going to actually write the probability that y is greater than 0.7 given x is 0.2 is 1 minus the probability that y is less than 0.7 given x is 0.2. And then by Bayes' rule, that is the probability that y is less than 0.7 given x is 0.2 is the probability that y is less than 0.7 and x is 0.2 over the probability that x is equal to 0.2. So the probability in the numerator here is essentially the probability that one dart goes in dx and 9 darts go between 0.2 and 0.7. So that the chance of that is 0.5 to the 9th power, because 0.5 is the distance from 0.2 to 0.7. The denominator, the probability that x is 0.2, now allows my 9 darts to go anywhere between 0.2 and 1. So that distance is 0.8. So I get 0.8 to the 9th power. So so that gives me my answer of 1 minus 0.5 over 0.8 to the 9th power. Same answer, just maybe a little bit easier. Here's the multiplication rule. So it's the analog of what we have in the discrete case. And I don't really have anything more to say about it. You just basically take Bayes' rule here for the joint density and just cross multiply to get the joint density. And so here's an example. Say x is gamma 2 lambda, and given that x is x, y is uniform 0x, find the joint. So we just use the definition here of the multiplication rule. So the conditional density is just 1 over x, because that is what it, you know, if you have uniform 0x, the conditional density is just 1 over x. And furthermore, since x is gamma, I can write out its density, and then when I take the product, the x's cancel, and you just get lambda squared e to the minus lambda x. Finally, the rule of average conditional probabilities. So in the discrete case, we have the probability of A is the sum of the conditional probabilities weighted by the probability that x is x for each one as x runs through all the different values of x. So the point here is I might not know the probability of A, and I may only know the probability of A conditioned on some other random variable. So for example, if A is the event if the second card in a deck is the king of hearts, say that I don't know that the probability of that is 1 over 52. So I could just condition on what the first card is, and I could run over all the different values of that first card. So there are 52 possible first cards. Of course, I say 52 there because one of them is that the first card would be King of Hearts and the second card would be King of Hearts. So the chance of that happening, of course, is 0. So excluding that case, you have 51 of these sums, a sum of 51 non-zero terms, and so it's 51 times so the probability of each of these products here is 1 over 51 times 1 over 52, so that gives us 1 over 52. So in the continuous case, the formula is the analog. Instead of sum, we have an integral here. Instead of probability that x is x, we have the probability that x is in dx, which is just fx x dx. So that's called the condition. That's called the integral conditioning formula. And so you can get some interesting results using this. So for example, if x is uniform 0, 1, so that's going to be referring to the probability of a coin flipping heads. And given that x is p, I have two Bernoulli p random variables, IID. Find the probability that the first toss is heads. So I'm going to condition on the probability of my coin tossing heads. In other words, x to be p, and p is going to run from 0 to 1. So now my conditioning. So my integral formula here is the integral from p is 0 to 1, and the probability that I get heads, given that the chance of getting heads is p, so that probability is obviously p, and the prior distribution here, fxp, is just 1, so it's the integral from 0 to 1 of p dp, which is p squared over 2, from 0 to 1, which is a half. So not knowing anything about this coin, the chance it's going to land heads is a half. Now, if I know that the first coin lands heads, then that's going to change what I know about the coin, and we'll see that the chance. So given that I1 is 1, we'll see that the chance that I2 is 1 is actually going to be 2/3. In other words, probability that I2 is 1, given that I1 is 1, is 2/3. It is not 1/2. So I2 and I1 are not independent, and we'll see why that's the case later. But let's just review a little bit of Bayesian statistics in the last couple minutes here. So remember, posterior is proportional to likelihood and prior. So let's understand what all these players are in terms of the example from above. So the likelihood is the probability of getting heads, given that the coin, the chance that the coin is heads is p. Of course, that is p. And my prior is uniform, so it's just 1. And so to compute the posterior, I have the posterior is likelihood times prior over this constant here. To find out where this formula comes from, you can just write out the multiplication rule 2 separate ways, and you'll see that the posterior is in fact 2p. So my prior initially is I have a flat prior that the probability that the coin lands heads is uniform.